These are the Chapter 2 Notes 4 on approximating binomial distributions and finding intervals on a normal curve. So today what we're going to do is we're going to use material that we've just talked about from Unit 2 on the normal curve to answer questions that we learned originally about in Chapter 8 where we talked about binomial distributions. So first of all, you're allowed to use information from our current chapter to answer questions from Chapter 8 if n is large. So if we're dealing with a problem where we're picking a large sample size, you're allowed to use information from Chapter 2 to answer Chapter 8 questions, at least as an approximation. Now, what does large mean? Specifically, n is large if these two formulas are true. If n times p, now remember p is going to be a probability, so p is going to be something small, between 0 and 1, right? If n times p ends up being greater than or equal to 10, and n times parentheses 1 minus p ends up being greater than or equal to 10, n has to be large enough so that both of these formulas work. So let's take an example to kind of see how this looks. Approximately 70% of Williamson High School students participate in spring athletics in a typical year. Let's say that 670 students currently attend WHS. Now, the first thing we're going to do is we're going to kind of double check to see what this real answer is. So based on what we learned about in Chapter 8, we're going to find the probability that more than 500 students will participate in spring athletics this year by calculating a binomial probability. So we're looking at more than 500 students. This is a more than problem. Remember, more than 500 students means we're going to start and count up from 501. It's not more than or equal to, it's more than. So we're talking about 501, 502, 503, so on and so forth. Our calculator does not allow us to count up from 500. So instead of counting up from 501, we're going to count down from 500. But then we're going to subtract from 1. So this is going to be one of these Binomial problems. We're going to count down from 500, but we're going to subtract that from 1 to get kind of our answer. So this is going to be a 1 minus Binomial problem. And remember, we always kind of start with our sample size, which is 670, our probability of success, which is 70%, and we're going to be counting down from 500, because then if we subtract that from 1, this value from 1, we'll get the probability of counting up from 501. So remember, on your calculator, we can do 1 minus, the Binomial command is found by going to second vars. And remember, you want to choose the one that says Binomial, not Binomial. So we're going to go to Binomial. On the newer calculators, it'll prompt you for your n value, your probability, and I think it calls it like the x value or the number of successes. If you have the older calculator, just type in those same numbers that we kind of wrote down earlier. We're going to separate them with commas. When you hit enter on your calculator, you'll get your answer, which is about 0.0035, and we'll write that number down right here. This is traditionally how we did problems like this. We just calculated the binomial probability. Let's see if we can use a normal approximation to answer the same question. To see if we can do that, we need to kind of see if these two formulas are true. So we're going to see if we can find an alternative way to do this problem, because sometimes these problems are a little tricky if we use Chapter 8 methods. So we're going to check to see if n times p and n times 1 minus p are both greater than or equal to 10. We'll start with n times p first. The n and the p values are just the sample size, 670, which seems to be pretty large, right? Times this probability. So we're going to do 670 times 0.7. And we'll see what we get here in just a moment. We're also going to check to see if n times 1 minus p is also greater than or equal to 10. So we're going to take 670 times 1 minus 0.7. If you just want to write 0.3, you can do that. Or if you just want to write it out like this, that's fine as well. So we have two calculations we need to make. We need to do 670 times 0.7. Hopefully that's bigger than 10, and it definitely is. 469 certainly qualifies as being bigger than 10. And if we do 670 times 1 minus 0.7, or 670 times 0.3, we get 201. A little bit smaller, but that also is greater than or equal to 10. So it looks like we can use an alternative method here. So what does this alternative method look like? Well, two things we need to calculate is we need to calculate a mean and a standard deviation. So the mean number of students participating in spring athletics, this is a binomial setting, so we can use the binomial mean formula that's on your yellow formula sheet. The formula for the binomial mean is mu is equal to n times p. So we just have to calculate 670 times 0.7, which we already did. That was equal to 469. Standard deviation, sigma, was equal to the square root of n times p times 1 minus p, also on your yellow formula sheet. So we're going to do 670 times 0.7 times 1 minus 0.7. If you have your graphing calculator with you, I would just crunch this out at one fell swoop. 670 times 0.7 times 1 minus 0.7. Again, that was 0.3. And the number we get is this decimal number. For right now, I'm not going to have you round this number. Because we're going to be utilizing all these decimal places in our next step. Part D is going to utilize what we learned in our previous class, which is finding the probability that more than 500 students will participate in spring athletics this year using a normal approximation and the values from step C. Show the 5 steps from our last class period in your answer. So what's this going to look like here? We're looking for the probability that more than 500 students will participate. And usually what we just say is we're looking for the probability that X is more than or greater than 500. I want to see where this would kind of fall on a bell curve at, so we're going to calculate this thing called the z-score, which we talked about in our previous class, which we get by taking the X value from the problem, which is 500, minus the mean, which is 469, divided by our standard deviation. And again, we haven't rounded this number. It's this 11.86170308 number. The nice thing about leaving this in your calculator like this is when you calculate this out, I'm going to put the 500 minus 469 in parentheses in the numerator. And then you can go divide by, if you choose the second answer feature, which is kind of down toward the bottom there, and hit enter, then you don't have to type in all that stuff. This is a z-score, so you might remember you can round this number because we're going to look it up on your green tables. And this is equal to 2.61 if we round it to the nearest hundredth. Step 1 is writing the initial statement. Step 2 is finding the z-score. Step 3 is rewriting the probability statement using the z value, which we just found. The greater than sign is one of the few things that stays kind of around. We're replacing the 500 now with the z-score, which is 2.61, and we're going to look up this value on your table A. So we need to find 2.61. It's a greater than problem, so if we look up 2.61 on our tables, it's going to look a little something like this. Let's see, we've got negatives over here, so let's go over to the second page of our tables. Here's 2.6. 2.61 appears to be about here. It's this 0.9955 number. And you could sketch the graph kind of as the last step or the second to last step. I kind of like throwing it in here first to get an idea of what this thing is going to look like here. So here's my graph. We're going to go 3 tick marks on each side. This is a greater than problem, so I'm going to go to 2.61 and shade over here. You can tell the probability we've shaded in isn't terribly big. Now, we stated earlier that this value here is this 0.9955 number. So that's referring to everything that's to the left of the line that we did. But I want to know what's this little region right here. So remember, if it's a greater than problem, we're always going to subtract this probability from 1. So we're going to do 1 minus 0.9955. And when you subtract these numbers, you get 0.0045. So we just answered the question using a normal curve, and what you'll notice is that this 0.0045 number is pretty close to the value that we got here. Now notice it's not the same, and don't expect to get the same value here. This is called a normal approximation. Approximation means it's going to be a guess. It should be approximately equal, and this is pretty close to 0.004, and the answer that we originally got, which is the more accurate or correct answer, is also around 0.004 as well. So it's a good approximation. It's not perfect, but I would say that they are pretty close. So besides doing normal approximation, a couple other things that you're going to be looking at today. Two types of problems you're going to be looking at today include finding the highest or lowest percent of data and finding the middle percent of data. Let's say that IQ is 100 with a standard deviation of 15. Find the highest 10% of all IQR scores. So I think you could kind of set this up using 5 steps as well. The first problem is I'm going to make a little graph of this. I'm going to shade in where the highest 10% would be. Now the lowest 10% would be like down here. But I want the highest 10%, so the region I'm looking at is going to be this region here. This region means that 10% of data is kind of in the shaded region, and the other 90% of data is over here. So this value where this tick mark is, the highest 10% corresponds to the 90th percentile because 90% of data is below this value. Step 3, we're going to look up this z-score. I want to figure out what tick mark this is, so we're going to look up 0.9000 on your tables. 0.9000 you won't find perfectly, but there is a value right here that says 0.8997. That kind of looks like it's at 1.28, I think. Yep, 1.28. So that's going to be the value that we're going to use right here. That's our z-score. We're going to substitute this z-score in for z. We know the mean is 100 and a standard deviation of 15, so we're going to plug those into our formula as well. And you're going to have to do some algebra to figure out what x is equal to. In this case, when you do the algebra, you're going to get 119.2. That's the value that we're looking for. Highest 10% of all IQ scores start at 119.2 and above because it's kind of shaded to the right. What if it's a middle set of data? Like the middle 40% of all IQ scores. I'm going to shade in the middle 40% right here. If you take away 100 minus 40, what you're going to get is 60. And if we split 60 in half, you're going to get 30% on each side. That means the percentiles we're looking for would include the 30th percentile, obviously, because we're talking about this 30% here. Where's the upper 30% at? Well, you can take 100% minus 30, that would give you 70. Or if you take 30 plus 40, that will also give you 70. So the percentiles we're looking up are the 3000 and the 7000 as well. These values should be kind of opposites on your table A. So if we look up 0.3000 or 0.7000, we should be able to find those values as kind of being opposites here. So when I looked up 0.3000, I didn't find it exactly, but I found 0.3015, which is pretty close. That corresponds with negative 0.52 on my little table sheet. So I'm going to use negative 0.52. And then the other value is at positive 0.52, so these are kind of the two values we're looking for. At this point, you're going to solve the same formula that we did last time. We're going to plug in 100 for the mean, 15 for the standard deviation. You've got to do a little bit of algebra and number crunching, and the answers you should get are 107.8 and 92.2. Those are the two values that we're looking for, so we'd say that the answer for this problem is between 92.2 and 107.8.